or you may say that R is equal to AR. So these two are equal. So note that this ring R contains A. A is an element of this ring R. A belongs to R. And this R is equal to AR, this particular set. So this A has to be equal to one of these. So let's write this thing. Now A belongs to R and R is equal to AR. Therefore, A is equal to AXI for some I. So this is what we had to say for some I. Let me show you that. A belongs to this particular set R and this set is equal to this particular set. So this A has to be equal to one of these. So A has to be equal to AXI for some I. This particular XI we claim is multiplicative identity. So in order to show this or to prove this, let Y belong to R. So let's take an element Y which belongs to R. Now let me show you again. Y belongs to R and this R is equal to this AR. So Y has to be something like A into x1 or x2, say xj. So let Y belong to R, then Y is equal to AXJ for some say j, for some j. Therefore, we have to show that particular xi we have already discussed. This xi is multiplicative identity. So we multiply y with xi. Therefore, y multiplied with xi is equal to axj multiplied with xi. Just note that we are dealing with a commutative ring. So multiplication is commutative. And this is equal to AXJ into XI because of associative law. And this can be written as A multiplied with XJ, XI into XJ because of commutativity of multiplication. And this is equal to AXI multiplied with xj because of associativity of multiplication. Now note that AXI is equal to A. So this AXI can be written as A and then into xj, and A into xj is equal to Y. Therefore, Y multiplied with xi is equal to Y. Similarly, we can prove that xi multiplied with y is equal to y. Hence, yxi is equal to xiy is equal to y. So therefore, this particular element we have found, this particular element xi is multiplicative identity in R. Therefore, xi is multiplicative identity in R. So what we have established is that a finite commutative ring with no zero divisors contains multiplicative identity. So R is finite commutative ring and this contains multiplicative identity. So if a ring is commutative, does not contain zero divisors and contains multiplicative identity, then that ring is integral domain. So we can say that therefore R is, let me write it in bracket, therefore R is an integral domain. Having said that, let's come to another proposition, and that says that proposition a finite integral domain, a finite integral domain is field. Let me recall what a field is. You have studied fields in your MSc or your undergraduate courses. A field is a set with two binary operations, so that let's say these binary operations are addition and multiplication. So conditions are the set is a abelian group under addition. Secondly, multiplication is distributed over addition. And thirdly, if we remove zero element from the set, then the remaining elements form an abelian group under multiplication. So I will repeat the definition at the end of this proposition. I just recalled your knowledge that a field is a set with the two binary operation. Under first binary operation, it is a abelian group. Second binary operation, multiplication, distributes over this particular binary operation under which it is a abelian group. And then if we remove identity element of first binary operation, we call it mostly 0, then the remaining elements of the set form an abelian group. That is, multiplicative inverses also exist in this particular ring. So this is definition of a field. You can say that do you remember what a Dewey ring is? In Dewey ring, we did not require that ring to be commutative. So we can say that a commutative Dewey ring is a field. We recall these things at the end of this particular proposition, and then let's prove that. So if a finite integral domain is a field, what is difference between integral domain and a field is that in integral domain we do not require multiplicative inverses for non-zero elements, but in a field non-zero elements are invertible with respect to multiplication. So let R be a finite integral domain. Let R be a finite integral domain. So this is a commutative ring with identity. So let R be a finite integral domain. Then we know that R contains multiplicative identity. Multiplicative identity, we write it as 1. Multiplicative identity 1. Let R is equal to, since it is finite, so we can write it x1, x2, x3, x4 and so on as above, xn. So let's choose a non-zero element. Let A belong to R and A is not equal to 0. So this is a non-zero element of ring R. We have to prove that inverse of A exists. Consider, multiply all the elements of this ring A with this ring R with A. AX1, AX2, AX3, so on up to AXN. Then we know that R and AR will be equal. Since A belong to R, therefore there exists, since A belong to R, so there must exist some element here. AX, let's say it AXK belonging to AR such that A is equal to AXK. And you can easily say that now. You can easily see that now XK is multiplicative inverse of A. Therefore, this particular XK is multiplicative inverse of A. Note that A was any non-zero element. So we have proved that non-zero elements of R are invertible. Therefore, non-zero elements of R are invertible, multiplicatively in fact, and therefore R is field. So finite integral domain is a field. Therefore R is a field. So we have proved that. I promised you to show you an example for a ring where when we multiply with non-zero elements do not become equal, and there are examples where it becomes equal. Let me give you an example. Note, consider Z6. You know Z6 is equal to 0, 1, 2, 3, 4 and 5. Let's take a non-zero element. Consider a non-zero element of Z6. let's say 3 belonging to Z. So let's take this element. We note that 3 is not equal to 0. But now see what happens. 3 times Z6 is equal to, multiply 0 with 3, this will be 0, 1 with 3, it will be 3, 2 with 3, it will become 0, 6 is 0. 3 with 3, it is 9, and 9 will be equal to 3, 3 into 4, 12, that is 0, 3 into 5, 15, and that is equal to 3 again. So note that this set is just 0 and 3. Number of elements, Z6 contained 5 elements, and 3 times Z6 contains only 2 elements. They are not equal. Let's take another example. Note, now consider Z7, and this is equal to 0, 1, 2, 3, 4, 5, and 6. And choose any element, non-zero element. Let's say 3 again. 3 belonging to Z7. Then 3 times Z7 is equal to 3 into 0 is 0, 3 into 1 is 3, 3 into 2 is equal to 6, 3 into 3 is 9, and that is 2, 3 into 4 is 12, that is 5, 3 into 5 is 15, that is 1, 3 into 6 is 18, and that is 4. Now note that Z7 and 3 times Z7 have same elements, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and same elements, 1 is here, 5 is, and so. So when we multiply Z7 with one of its non-zero element, result is Z7. But when we multiply Z6 with one of its non-zero element, result is lesser than Z6. Reason is Z6 is not an integral domain. Z7 is an integral domain. Z6 contains 0 divisors. Z7 does not contain 0 divisors. This was the reasoning I was telling you at this particular step. When I was saying that let R be finite, x1, x2, x3, so on up to xn, and R does not contain 0 divisors, with no 0 divisors. Since there are no 0 divisors, so if we multiply it with a non-zero element of this particular ring, result will be same. These two sets will be exactly the same, as these two sets are exactly the same. But if there were 0 divisors, then they may be different. So note that if the ring does not contain 0 divisors and you multiply all the elements of the ring with the one of the non-zero elements, then you will get the same elements again. So this is what I promised to you that I will explain. So remember that the result we have proved is that a finite integral domain is a field. Let me recall the definition of field. Let us recall the definition of field. A ring R with identity, with multiplicative identity, is field if you remove zero element from the ring, then the remaining elements is commutative group. Is commutative group. So this is the one definition. A ring R with identity is field if R less 0 is commutative group. Or you can say that a commutative ring R with identity is field if you remove zero element from the ring. This is group. We don't need to say commutative because we have said that the ring R is commutative. So if you remove zero element, resulting non-zero elements will form group. Or you can say that a commutative division ring, a commutative division ring is a field. And examples of field, there are many examples. R, the set of real numbers, this is field. Q, the set of rational numbers, this is a field. C, the set of complex numbers. All these are fields. Note that Z minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on. This is not a field. Is not a field. Why? You have to think about that. Why it is not field? Why set of real numbers is not a field? This is for you to think. So set of integers is not a field. We have proved that a finite integral domain is a field. So let's see that a finite integral domain is a field. So if we are given an integral domain which is finite, it should be a field. So in order to prove that a ring is field, it is sufficient to establish that it is integral domain and then it is finite. Yes. So let's see a property of a concept which is called in fact Boolean rings. Let's see what Boolean rings are. Boolean rings. Let me define it first. Definition goes as follows. A ring or with identity is called Boolean ring if a square is equal to a for all a belonging to R. So a ring is a Boolean ring if a square is equal to a for all the elements of the ring. So let's have a proposition. Proposition. Let R be a Boolean ring. Let R be a Boolean ring. Then number one, a plus a is equal to 0 for all a belonging to R. And secondly, R is commutative. Commutative with respect to multiplication. R is commutative. R is commutative. So let's prove that. For proof, first of all, we will establish that a plus a is equal to 0 for all a belonging to R. So to prove that, in fact, we will need two elements of the ring. To begin with, we will take two elements of the ring R. Let a b belong to the ring R. Then, since R is closed under addition, a plus b belong to R as well. And therefore, property of Boolean ring is square of each element the same element. So therefore, a square is equal to a, b square is equal to b, and a plus b is also an element of R. Therefore, a plus b square is equal to a plus b. Now, let's consider a plus b square. A plus b square is equal to a plus b multiplied with a plus b. Remember that we are not given that R is commutative. We have to prove that R is commutative yet. So we have to be very careful about this multiplication. A multiplied with a is a square. A multiplied with b is ab. Then b multiplied with a is ba. We cannot write it 2ab because ab and then ba. This may not be equal to 2ab. And then b multiplied with b is b square. And therefore, now a plus b square is equal to a plus b. Therefore, a plus b is equal to a square is equal to a. So this is a plus ab plus ba, and then plus b square is equal to b. Now, this a will get cancelled with this a, and this b will get cancelled with this b. So we are left with 0 is equal to ab plus ba. AB plus BA. Let's call this 1. So AB plus BA is equal to 0. Note that we may choose A and B equal with each other. So let A is equal to B, then 1 becomes, let me show you what 1 is. This is 1. AB plus BA is equal to 0. So when we take A is equal to B, so this B is A again. This B is again. So putting B is equal to A, 1 becomes 0 is equal to A into A plus A into A. Note that. B is A again. B is A. So 0 is equal to A into A plus A into A. And therefore 0 is equal to A into A is A square plus A into A is A square. And therefore 0 is equal to A square is equal to A. A square is equal to A. And therefore we have proved that A plus A is equal to 0. So this was the first condition we had to prove. For second condition, we have to prove that R is commutative. In order to see that R is commutative, first we note that from 1 AB plus BA is equal to 0. From 1 AB plus BA is equal to 0, and therefore BA is equal to minus AB. Let's call it 2. BA is equal to minus AB, and we can write it minus A multiplied with B. From 2, let's call it 3. From 2, A plus A is equal to 0, and therefore A is equal to minus A. So it means minus A is equal to A. Put this in 3. Put in 3. Therefore, BA is equal to minus A. Write A for minus A is equal to AB. So AB is equal to BA. So therefore, R is commutative. So a Boolean ring is always commutative. Let's see an example of Boolean ring. Let R be a non-empty set. Let X be a non-empty set. X be a non-empty set. Consider power set of X. You know that what power set of X is? Power set of X means set of all subsets of X, which contains X as well, which contains empty set and all the subsets of X. So consider power set of X. We define for any two subsets AB of X, AB belong to power set of X, we define, see how we define a plus b. We define addition as follows: a plus b is equal to a complement or a intersection b complement. You can write c or you can write just this dash: a intersection b complement union a complement intersection b. So we define addition in this way, and we define multiplication of any two subsets a and b as just their intersection, a intersection b. Then with these operations, px, power set of x, becomes a Boolean ring. A Boolean ring. Under these operations, px is Boolean ring. And you can check it by yourself on your own. I give you a little assignment. It will help you in understanding that. So let's have an assignment. Now we come to number 19. Assignment. Assignment goes like as follows. Consider px as Boolean ring. Let x be a non-empty set. Consider px as Boolean ring. With the operations I have just told you, that is a plus b is equal to a intersection b complement union a complement intersection b, and a multiplied with b is a intersection b. So with these operations, px becomes a Boolean ring. You can check it by yourself. It is not very lengthy, but you can do it easily. So your assignment is prove that with above definition of addition, prove that a plus a is equal to empty set, and a plus empty set is equal to a, and a multiplied with x is equal to a. So this is your assignment. You have to do it on your own. So this was about Boolean rings. Let's come to a very simple concept, that is about characteristic of a ring. Characteristic of a ring. So this is a very simple concept. Let me give you an example. Consider, let's say, consider Z9. You know Z9 is 0, 1, 2, 3, 4, 5, 6, 7, 8, and operations are addition modulo 9 and multiplication modulo 9. We have to add and then divide by 9 and accept remainder only. Then we have to multiply and then divide by 9 and to accept remainder only. So consider Z9. We note that if we multiply 9 with 1, 1 is multiplicative identity. Result will be equal to 9. And you know that in this ring 9 is 0. 0 means 9 is congruent with 0 mod 9. We say that 9 is 0. So characteristic of this ring Z9 is 9. Therefore, characteristic of Z9 is 9. So characteristic is the least positive integer which when multiplied with the multiplicative identity gives 0. So let me define that. Definition. So note that when we define characteristic, the ring has to be a ring with identity. So the ring has to be a ring with identity. So characteristic of a ring with identity is the least positive integer such that that positive integer multiplied with 1 gives you 0. So definition, let R be a ring with identity then the characteristic of R is defined as the least positive integer. Remember that the least positive integer, n such that n multiplied with multiplicative identity is equal to 0, as 9 multiplied with 1 is equal to 0 in Z9. So characteristic of Z9 is 9. Let me write the example. Can you guess what is characteristic of? What is characteristic of Z6? It is 6 because 6 is the least positive integer, for which 6 multiplied with 1 is equal to 0. In fact, means congruent mod 6. It happens that in certain rings, you cannot find a positive integer so that when it is multiplied with 1, you get 0. For example, in Z, set of integers as a ring, consider ring Z, you know that this is -3, -2, -1, 0, 1, 2, 3, and so on. Here we cannot find positive integer. Remember that we cannot find positive integer n which satisfies above condition. What is that condition? N multiplied by 1 is equal to 0. This is not possible. This is not possible in Z. Is not possible in Z. So we cannot find a positive integer which when multiplied with 1 gives you 0 in the ring of integers. In such case, we say that characteristic of Z is 0. We say that, or we define that characteristic of Z is 0. Let's note again. Similarly, each of following rings have characteristic 0. R, the ring of reals, Q, the ring of rationals, C, the ring of complex numbers, and so on. You can think about other rings. If you like, you can think about ring of quaternions. What is characteristic of ring of quaternions? You can think about this on your own. Let's have a proposition. We were at number 22. We come to number 23. And the proposition is, if R is an integral domain, let's have a proposition. If R is an integral domain, having characteristic n, having characteristic n which is not equal to 0, having non-zero characteristic, then n is prime. So please note that what we are saying. We are saying that if an integral domain has non-zero characteristic, then that characteristic is a prime number. So for proof, let R be an integral domain and let n not equal to 0 be, let n not equal to 0 be characteristic of R. We have to prove that n is prime number. So we have to prove that n is prime. N is prime number. We will prove this by contradiction. On contrary, suppose that n is composite. You know what composite numbers are. 6 is composite because we can write 6 as 2 into 3. Then n can be written as R multiplied with, this is multiplication, multiplied with S, where both R and S are greater than 1. So this is property of composite number. Since n is characteristic of R, therefore n multiplied with 1 is equal to 0. This is definition of characteristic. Now n is equal to R into S. So therefore R multiplied with S multiplied with 1 is equal to 0. And therefore you can write it R multiplied with 1 into S multiplied with 1 is equal to 0. Though now here is very important observation you have to make, and that is 1 is element of this ring R. 1 is element of the ring R. So R times 1 also belong to R. Remember that. 1 belong to R. So 1 plus 1 belong to R. 1 plus 1 plus 1 belong to R. So R times 1 plus 1 plus 1 will belong to R. So now R into 1 belong to R. S into 1 belong to R, and R is integral domain. And R is integral domain. Remember that integral domain is a ring which does not contain zero divisors. What does this zero divisor mean? Non-zero elements, so that if they get multiplied with each other, they give 0. But integral domain does not contain zero divisors. So since R is integral domain, R cannot contain zero divisors. So R multiplied with 1 and S multiplied with 1 is equal to 0, and R does not contain zero divisors. So R multiplied with 1 and S multiplied 1, these both elements cannot be equal to non-zero. One of them has to be 0 in order to get 0, because R does not contain zero divisors. Therefore, either R into 1 is equal to 0 or S into 1 is equal to 0. Therefore, either R is equal to 0 or S is equal to 0. This is contradiction, because R and S, each one of them is greater than 1. So they cannot be equal to 0, which is contradiction. Because each one of RS is greater than 1. So our supposition is wrong. Therefore, N is prime. We suppose that N is composite. So N is not composite. Therefore, N is prime. So we approve that characteristic of an integral domain, if it is finite, if the characteristic is finite, then it has to be prime. Let's have an observation or a note. In fact, I'm using this condition again and again. An integral domain is a ring with identity, a commutative ring with identity which does not contain zero divisors. Let me recall it. An integral domain R is a commutative ring with identity which does not contain zero divisors. Zero divisors, non-zero element, so that their product is equal to 0. As in Z6, 2 and 3 are non-zero and their product is 0. So 2 and 3 are zero divisors in Z6. So how do we determine that a ring is integral domain? Or if a ring is integral domain, what is the condition? So working condition is this is a working condition. If product of two elements of the ring is equal to 0, then either A is equal to 0 or B is equal to 0. If R is an integral domain and we find that product of two elements is equal to 0, then either of them must be equal to 0, because both cannot be 0 at the same time. So working condition AB is equal to 0 implies that A is equal to 0 or B is equal to 0, where AB belong to R. So let me say it again. An integral domain R is a commutative ring with identity which does not contain zero divisors. So if AB belongs to R and R is integral domain, and R is integral domain, then if product of AB is 0, then either A is equal to 0 or B is equal to 0. So this is working condition in order to find whether a ring, this is a working condition if we are given elements of an integral domain. So we use this condition quite often when we do proofs. So this was about characteristic. Let's do little bit more about characteristic. In fact, we have a proposition which says that let's have an observation about binomial theorem. An observation about binomial theorem. You know about binomial theorem. You say that a plus b raised to power n is equal to a raised to power n, then plus n1 a raised to power n minus 1 into b raised to power n, then plus n2 a raised to power n minus 2 b raised to power 2, and then n is a finite number, please remember that, plus at the end you get b raised to power n. Let's assume that the elements a and b belong to an integral domain. Let us assume that these two elements a, b belong to R, where R is integral domain. So let us assume that AB belongs to R, where R is integral domain, and its characteristic is of characteristic, and you know that this characteristic, if it is finite, should be prime. Of characteristic of prime, and say that prime is P. So having said that, let's replace this n by P. Then we have a plus b raised to power p, p is prime. Instead of n, we are writing prime p is equal to a raised to power p plus p1, a raised to power p minus 1, b plus p2, a raised to power p minus 2, b square, and then plus 1 up to b raised to power p, where p is a prime and p is characteristic of the ring R, which is integral domain, and A, B, these elements belong to this particular integral domain. So having said that, note that, let me show it again. You know that what this P1 is? P1 is just P. and P2, this is P into P minus 1 upon 2 factorial into P minus 2 factorial. You know these things, P minus 2 factorial and so on. What point I want to make is that P is a factor of P1, P is a factor of P2 and so on. This prime P is factor of each one of these before B raised to power P. P is a factor of, let me write it in this form the way you write it in your FSC. This is equal to A raised to power P plus, in terms of sigma notation, this is sigma. R varies from 1 to P minus 1. A raised to power R. R varies from 1 to P minus 1. At the end we will have B raised to power P minus 1. So we are going to write here as B raised to power 1 and A raised to power P minus 1. Please check it if it is correct. We put R is equal to 1. This is R. So this is P minus R. This is correct. So A raised to power P minus 1, B raised to power 1. And here we have PR. So this is what I want to say. And at the end we have plus B raised to power P. So this is what I want to say. A raised to power P plus sigma R varies from 1 to P minus 1 PR A raised to power P minus R B raised to power R, and then at the end we have B raised to power P. So A raised to power P and then P1 A raised to P minus 1 B raised to power 1 plus so on A P2 A raised to P minus 2 B2, and then so on. At the end it will be P minus 1 A raised to power, it will become 1, and then B raised to power P minus 1, and there then B raised to P. It is correct. So you can write it in this way. I don't know why I indulge this, but anyway it is okay. So this is a binomial expansion, and what point I wanted to make was this P1 is divisible by P. P is a factor of this P1. P is a factor of this P2 and so on. I wrote it for this purpose that P is a factor of PR. P is a factor of PR here. So we note that as P is prime, therefore P is factor of P1, P2 and so on. It is up to P minus 1. So P is a factor of all of these. So what does this mean is that when you will simplify it, it simplification will contain p. Its simplification will also contain p until b raised to p minus 1. All the terms before this particular term, all the terms contain p as factor. Let me write it. All the terms before b raised to power p contain p as a factor. Let me write it for your understanding. For your understanding, expand a plus b raised to power 7. 7 is prime. And get the point. Expand a plus b raised to power 7 by binomial theorem, and you will see that after first term and before last term, each term will have 7 as a factor because 7 is prime. Each term will have 7 as a factor. So do it on your own to make your understanding better. Anyway, having said that, each of these terms is going to have p as a factor, but p is characteristic. P is characteristic of R, so that P multiplied with 1 is equal to 0. So having this observation, note that each of these terms is going to have P as a factor, and you can write that P as P into 1, and that P into 1 will be equal to 0. So all these terms will vanish. Therefore, all the terms in between a raised to power p and b raised to power p will vanish. For this reason, and therefore, if R is an integral domain, P is characteristic of R, and AB belong to R, then A plus B raised to power P will be equal to A raised to power P. All the terms in between will vanish, plus B raised to power P. So this is very important observation. Having observed this, let's come to a proposition. So this is number 26. So proposition says that this is about integral domain. So proposition, let R be an integral domain with prime P as its characteristic, then A plus B raised to power P, and then P raised to power K. Note that this is P raised to power K is equal to A raised to power P raised to power K plus B raised to power P raised to power K. So for any AB belonging to, for all AB belonging to R and any integer K greater than or equal to 0. So let's come to proof of this particular proposition. So for proof, so condition is for K greater than or equal to 0. Note that if we take K is equal to 0, then A plus B raised to power P raised to power 0 is A plus B raised to power 1 is equal to, it will become A plus B is equal to A plus B. It is just trivial because when you put K is equal to 0, P raised to 0 will become 1, this will become 1, this will become 1, A plus B raised to 1 is equal to A raised to 1 plus B raised to 1, which is just obvious. So let's make this observation for proof. Number 1, if K is equal to 0, then A plus B raised to power P raised to power K is equal to A raised to power P raised to power K plus B raised to power P raised to power K. These two are equal trivially, because this means A plus B raised to power 1 is equal to A raised to power 1 plus B raised to power 1, which is obviously true. So for K is equal to 0, it works. For K greater than 0, we will use induction. So for K greater than 0, we will use induction. We will use induction. And you know the steps for induction are, first of all, we will prove that the result is true for K is equal to 1. Then we will suppose that result is true for certain value of K and prove that the result is true for immediate value after that particular certain value. So at your level, this is very simple thing. For K is equal to 1, we have to prove that. For K is equal to 1, we note that left hand side is equal to A plus B raised to power P and K is equal to 1. This is equal to A plus B raised to power P, and we know